We saw this function a couple of videos ago, and I wanted to graph it. I think it's a very interesting graph. Anyway, so graph y equal to cube root of x squared minus x minus 6. And as you would in calculus, we should convert this to exponent form. So that'd be x squared minus x minus 6 to the 1/3 power. So I know the first derivative didn't look too bad. The second derivative, we'll have to see. Sometimes when you get a derivative or a second derivative that looks really long, but if you're done taking derivatives, then and you need to set it equal to 0, there are a lot of ways where you can just simplify and solve the equation that don't involve first simplifying the big algebra expression. So maybe that'll happen this time. We'll see. All right, well, first of all, what's the y-intercept? So the y-intercept is y at 0. So just plug in 0, and it's a cube root of -6. Cube root of -6, and yes, you can take the cube root of a negative number, and because it's going to be negative. So what is it? I think we should estimate it, because we'll want to plot that on the graph, so we need some kind of decimal estimate there. So I'm just going to do 6 raised to the parentheses 1 divided by 3. I could have made it -6, but I know it's going to be a negative number. So I'm punching in 6 to the 1 divided by 3. All right, so anyway, I get 1.82. It's around 1.8. So it's around -1.8, right? So as far as graphing goes, most of the time we just go one decimal place if you're lucky, and so that'd be good enough to estimate it as far as graphing purposes. All right, well, that was fairly easy. What about y-intercept and or x-intercepts? Okay, the roots. The roots of the equation are the x-intercepts. So the roots are, all right, well, to get the root, we set the function equal to 0. And without doing calculus, I kind of like to work in the radical form of it. Well, if you cube both sides, basically, you're interested in where is the inside, called the index. No, not the index, the radicand of the radical. Where is that equal to 0? And I rigged the problem so that it would factor nicely. X minus 3, x plus 2 equals to 0. So again, we're solving by factoring, and set each factor equal to 0. In case you're still a little rusty at this stuff, so x would be 3 and -2. That's what makes that function equal to 0. So the roots are x equal to 3 and -2. 3 and -2. So, okay, asymptotes. Does it have any asymptotes? Well, no, because the cube root, for example, the cube root's domain is the entire real numbers, which means you can plug any number in the cube root, including negative numbers. So now if that was square root, we would have to stop where the square root is equal to 0. That would be, because when the square root is negative, even though the square root of negative is a complex number, we're not graphing complex numbers here. We're graphing in the xy plane. And so, but cube roots exist everywhere, and so there's no division by 0 or anything else that's going to stop this from it's going to cause it to create a vertical asymptote. As far as horizontal asymptote, that's when the limit goes to infinity, and it's going to go to infinity. When x goes to infinity, this just blows up, and cube root still goes to infinity. So there are no asymptotes. So I just put no asymptotes. All right. So there's our initial information. Now let's look at the derivative. And I'm going to work the derivative here and then copy it neatly there. So using this form, y prime would be 1/3 parentheses x squared minus x minus 6 to the minus 2/3, and then chain rule. Don't forget chain rule. Got to multiply by 2x minus 1. All right, and And so that would be, well, that would be 2x minus 1 over 3, parentheses x squared minus x minus 6 to the positive 2/3 power. That's supposed to be a 2/3. So I'll write that over here. Y prime equals to 2x minus 1 over 3 times x squared minus x minus 6 to the 2/3. Now, normally on a big classroom board I would just write underneath this. But I'm kind of, hamstrung for space here, as you can tell. So I want to find out what are the critical numbers of this, of the function. The critical numbers are where either the first derivative equals to 0 or where it's undefined. And it will be undefined because we have a denominator that can be 0. So anyway, if I set this equal to 0, then I'm solving the numerator. Solving for the numerator. The numerator has to be 0. And so 2x minus 1 equals to 0. X would be positive 1/2, right? Add 1, divide by 2. So the critical numbers are x equal to 1/2. And now we have to think about the denominator. When the denominator equals to 0, then we will have division by 0. And we've already solved for that, haven't we? If I divide by 3, the 3's cancel. If I raise to the 3/2 power, that cancels, because dividing 0 by 3 gives you 0. Raising 0 to the 3/2 power to cancel a 2/3, still going to give you 0. So basically I'm solving this, and that tells us we worked that out earlier when we found the roots. X equals to, 3 and negative 2. Alright, so those now cause division by 0. And so the critical numbers are also 3 and negative 2. So I have 1/2, 3, negative 2. Now here we expect vertical asymptotes. Vertical asymptotes. So let me just write that for the moment here. Vertical. No. Not vertical asymptotes. There are no asymptotes. What do we call that? Vertical tangent lines. Okay. In other words, it's going to be like this, where the tangent line has an undefined slope. So how about we put undefined slope? I'll abbreviate undefined for those two numbers. All right, so make that for your notes. I'm going to end up erasing it because I need to, save space here. Okay, now then, let's. We got the first derivative down, and found the critical numbers. Now let's go for the second derivative. That's going to be fun. So let's see. Y prime equals to this without the equal 0. So I have the first derivative up here, so I can reference it. And now we're going to take the second derivative. That's going to be a little messier, I think. So y double prime will be, I'll tell you, let me start to the left here. Make sure I got room. Oh, I don't think it's going to be that bad, but it'll be a little bad. Alright, so we have the quotient rule. Derivative of the numerator is 2 times the denominator, 2 times 3, x squared minus x minus 6 to the 2/3 power, minus the derivative of the denominator times the numerator. Alright, so this derivative is 2/3 times 3, that's just going to be 2, times x squared minus x minus 6 to the, subtract 1 from 2/3, we get minus 1/3. And then also, let me make that look more like a 3. Okay. And then we multiply by this derivative, do the chain rule, times 2x minus 1. And then we multiply by the numerator, which happens to be 2x minus 1, doesn't it? And then everything is divided by the square of the denominator. All right, so if I square this, I'll get 9. If I raise this to the second power, I'll get 4/3. Okay, so it's x squared minus x minus 6 to the 4/3. Oh, okay, now that's a mess. That's a mess. Well, let's see. All right, well, this is going to take a little room here. I'll have to somehow fit it on this board. First of all, I think I will clean this up. So y double prime is 6 times x squared minus x minus 6 to the 2/3 minus 2 times x squared minus x minus 6 to the negative 1/3 times, and these are squared, 2x minus 1 squared, divided by this whole mess, 9 parentheses x squared minus x minus 6 to the 4/3. Okay, and here's what I want to do, because this cube root stuff makes it look pretty messy. So I'm going to multiply top and bottom by the positive cube root of this term. So this is, I'm out of room, so let me put parentheses to the 1/3 over parentheses to the 1/3. All right, which is x squared minus x minus 6. So otherwise I would normally write it out. All right, so when I chose that because I wanted this to cancel. And unfortunately, this will make this a 1. First power, because 2/3 plus 1/3 is 1. And then this will be like a 5/3. Okay, so the second derivative then becomes, so I think it actually was necessary to do some simplifying here to make this a lot easier. Okay, so let me erase this, and I'll see what happens. We'll go up here. Alright, so this, yes, it is a lot of work, isn't it? Graphing could be a lot of work. But you'll learn a lot from graphing. I think it's absolutely worth it. And besides, that's at every calculus course in the land. So, alright, so if I multiply here, I'm going to get first power. So y double prime up here is going to be 6 parentheses x squared minus x minus 6. Okay, and then this will cancel, leaving a 0 power, which would be, the parentheses to 0 would be 1. And then I have minus 2 times 2x minus 1 squared, divided by, this will be now 5/3, 9 parentheses x squared minus x minus 6 to the 5/3. There it is, our beautiful second derivative. Okay, well, oh, before I erase it, I better check it. Yeah. I think that's good. So, at this point, if I made a mistake, I'd have to just reshoot this whole video. That would be, that'd be time consuming. Okay. All right. Now then, bet you wouldn't know about my screw up, would you? If I had to reshoot it. All right. Well, let's talk about this. For the second derivative, there is division by 0 down here, and but there's division by 0 here, and so I'm not going to worry about it, because these are interesting points. So we go to set up our number line to look at the interesting points. We'll have these numbers. Now we might have to add some more up here. This is 3. Alright, so already these 3 critical numbers divide this up. And so we'll have to check the second derivative on either side here. So I'm not going to worry about that denominator ever equaling 0 for the second derivative. Could it cause a change of concavity when you cross it? Yes, I think it could. So if I don't worry about this, I just set equal to 0. And if I'm not worried about this being 0, then I can just cancel it. In solving the equation, that is, set equal to 0. And, oh boy, you know what? Before I do some erasing, I better write that second derivative. Y double prime was equal to 6 parentheses x squared minus x minus 6 minus 2 parentheses 2x minus 1 squared over 9 parentheses x squared minus x minus 6 to the 5/3 power. There we go. Alright, so this was what I had up there. I hope you can read it, but you should have it in your notes. Okay, so where do we go from here? So I'm ignoring the denominator. I want to know where the numerator is equal to 0, because when a fraction equals 0, the numerator has to equal 0. So I need to multiply all this stuff out. So just think of this chunk here, and I've got, multiply here, I got 6x squared minus 6x minus 36 minus 2. And when you square this, you know, it's 2x minus 1 times 2x minus 1. 4x squared. Minus 2x is minus 4x, and then plus 1. All equals to 0. You know, I could have helped myself by dividing everything by 2 first. You know what? Let's do that. Let's do that. If I divide by 2 or multiply by half, I'll cancel this 2 and that 6 will become a 3. So I actually end up with, let's see, there's a red pen here. Alright, when I do that, then I'm going to end up with 3 here and nothing there. Alright, so that would make way more sense. On the right side, 0 times a half is still 0, so that doesn't change. Alright, now we'll try this again. So multiply this out. I have 3x squared minus 3x minus 18 minus parentheses, and we multiply that out as 4x squared minus 4x plus 1 equals to 0. Alright, so let's combine terms. 3x squared minus 3x minus 18 minus 4x squared plus 4x minus 1 equals to 0. You know, not a lot, but some calculus students really mess up algebra in here. I think they're going too fast, being a little careless. And I'm in a habit of just looking my stuff over, trying to catch my errors, which I can usually catch my errors. Let's see. Actually, so far, all these videos I shot for this course up to this point, I've only had to redo one where I made a really dumb error that I never fixed, never caught when I was working the problem. And I usually catch my errors. And you should too. You should too. Get in the habit of proofreading what you're doing. Alright, so let's see. We have minus x squared. And 4x minus 3x is plus x. And then minus 19 equals to 0. Okay, well, let's multiply by negative 1. That gives me x squared minus x plus 19 equals to 0. Alright. Oh boy. Well, I don't think there's an answer to that one. Because we can use the quadratic formula on it. It's not going to factor. If we use the quadratic formula, here's what it's going to start to look like. X would be minus negative 1 minus b plus or minus the square root of b squared minus 4 times a times c over 2a. What we have here is a negative, big negative number. Negative, I don't know what it is. Negative 75 maybe. I guess minus 75. Anyway, it's a complex number. There's no real solution there. And so you would have to say that this function has no inflection point. Because the numerator doesn't equal 0. And in a way, these two roots of the first root, it may be inflection-like, but the slope is undefined here, so I don't think it's technically defined as inflection. But there's no other points that would qualify as inflection points. So I'm going to declare no inflection points. Let me see, erase this stuff. And I'll tell you what I'm going to do. I'm going to condense all my work over here, okay, to just what we need. And then, because I'll give you more board space to work. So anyway, you might pause the video and try to graph this yourself. See what you do, see how it comes out. Test yourself as you're learning here. That would go a long way. If you just sit back and watch my videos, and I don't know how much that's going to sink in. Now, if you're writing as I'm talking, writing this stuff down, taking notes, a lot more is going to sink in. But if you pause the video, try to work this best you can, based on what you see, you can learn a lot that way. So, all right, so I'll be back in a second or two. Well, that was fast, wasn't it? Okay. Well, I condensed all the information on the left side, and boy, I sure hope you're not watching this on a little iPhone or something. You should be watching this on like a laptop and with a big screen. But anyway, let's read through it. Here's the original function. You've got that down. The Y-intercept was around negative 1.8. Roots are 3 and negative 2, where it crosses the x-axis. We found no asymptotes. The first derivative I wrote in the radical form, 2x minus 1 over 3 cube root x squared minus x minus 6. And the critical numbers are at 1/2, which is where the numerator is 0, and where the denominator equals 0 is 3 and negative 2. Also critical numbers. And then finally the second derivative, I went ahead and simplified that on top. Minus 2x squared plus 2x minus 38 divided by 9 cube root of this mess to the 5th power, 5/3 power. And we found there were no inflection points to that. So there's all our all our basic information. Okay, now let's see what happens here. I'm going to kind of map it out down below here, and I'll draw the graph up above. So, okay, let's see. We have what do we got? Well, the critical numbers, and there are no inflection points, so there really are only 3 numbers to put on this: minus 2, and 1/2, and 3. And here is y prime, there is y double prime. So I'm going to stop myself for a minute and make sure that I'm catching this all on the bottom of the camera. Well, that worked out good. I see everything's on the screen here, so I was afraid of going a little too low. I have to adjust my camera up and down, and sometimes I'm not quite sure how low I can write. All right, so look what I did here. We have critical numbers. And we have no official inflection point, although I think inflection might change at negative 2 and 3 because it's undefined there. Matter of fact, I'm going to put, just a matter of taste, I'm going to put, little open circles here to indicate that the derivatives cannot equal to these 2 numbers. All right, and a solid point means it does equal to 1/2. I don't know if that's going to do much for us, but anyway. All right, now we just have to figure out what the signs are. Yeah, where are the first and second derivatives positive and negative? And that will map out the shape of the graph. And it's a little bit of work. I'm going to use my calculator a bit here. And so, let's make it easy. So I'm going to punch in, first of all, my function. So parentheses, 2x minus 1, and then divide by 3, and then divide by the x squared minus x minus 6, close parentheses, raised to the left parentheses 1 divided by 3. All right. I would show you my calculator screen, except I've got the focus on manual. It won't focus on the camera, and I don't want to mess with that. So, all right. So 2x minus 1 parentheses divided by 3, also divided by x squared minus x minus 6 to the 1/3 power. All right. So I'm going to pick numbers that are not one of these 3 numbers. For example, how about negative 3? So I'll store negative 3. Negative 3, store x. Then I'll bring up that other calculation, and I get minus 1.284 something. We don't care what the number is. If I put negative 3 in, or any number over here, I'm going to get a negative number, which means the function is decreasing. All right, well, I'll do something like that here. Now here, if I put 0 in, you could probably do that in my head. I think it's going to be positive. Yeah, it's a positive number, so 0 is between -2 and 1/2. Any number you plug in here should come out to be a positive, so it does increase here. And then what's a nice number between here? How about 1? 1 store x. Oops. 1 store x. All right. And I'll check it through. That's a negative number. Minus, so that's decreasing. And finally, if I pick a number greater than 3, will it increase? We'll find out. So 4 store x. I think there's some symmetry to this graph. So it probably will be a positive. Yep, positive. Plus. Alright, so it's going to decrease, increase, decrease, increase. Alright. They don't always alternate signs, but you know, often they do. Alright, now I got to plug in my second derivative. And, oh boy. Alright, so left parentheses, -2x squared. Are you trying this on your calculator? Yeah. Use that technology. It's nice. Alright, so -2x squared plus 2x minus 38 in parentheses. And then I'll divide by 9. I don't really have to divide by 9, but I will. Because we're only worried about the sign, not the exact number we get. So divide by 9, divide by left parentheses, x squared minus x minus 6, close parentheses, raised to the left parentheses 1 divided by 3, close parentheses. Got all that? I'm just looking at all my stuff here. Make sure I didn't screw up anything. I think it looks good. Oh, raised to the 5/3 power. That's my screw up. 5/3. I don't think that's going to matter, but anyway, I'll get it right. 5/3. All right, so I'll do the same strategy here. I'll plug in -3, then run it through the second derivative, and I get a negative number. So over here, it's second derivative is negative, it's concave down. And then if I plug in 0 and run through, I'll get a positive number. So it's concave up. So it did change. You know, where the second derivative is undefined, it did change concavity. All right, that's not always guaranteed, but it did this time. Now I'll plug in 1 store x, and run that through. I get a positive number, so it's still concave up, and then presumably we'll get a negative over there. I'll use 4 store x. You can use 5, you can use anything really, as long as it's greater than 3. And I got a negative. It's concave down. There we go. Okay, so I love the analysis of this. It's yes, it's a very tedious problem, but the analysis is very, very interesting. Okay, well, let's see. We need to graph this thing and see. We kind of run between -2 and 3, but we should go to the left a little bit, to the right a little bit, and so what should I do here? How about here's -3. 1 minus 1, 2, 3. And I'm not sure how far it's going to go up on the vertical. We should plug the interesting numbers in. For one thing, should I graph this? I'll graph it in green, I guess. Green's pretty dark color for me right now. So the roots are 3 and -2. So across here, across there. And I'll worry about the Y-intercept here in a minute. Now the only other interesting number is 1/2. So, but it's not a root. I'll have to calculate for 1/2. So go back to the original function. Okay, and there we go. Got all my stuff. Let's see, 1/2 is 0.5. 0.5 store x. So I'm plugging in this critical number because I want to know where it graphs. But again, I've seen people plug it into here and they graph it. Wait a minute. No, we're graphing this function. We're not graphing the derivative. The derivative is a tool. All right, so let me see. I've got x squared minus x minus 6. That's negative 6.25. Now if I raise that to the 1/3 power, I'll get a negative 1.84. About 1.84. It's a little bit different from this one because mine was minus 6.25, 6 1/4. So the 1/2, where should we put it? So let me just add up here that y at 1/2 is approximately minus 1.84. Okay, so we're not going to be able to tell much difference between these, are we? Alright, so how about we go down to 2, and I'll go up here to 2 as well. Okay, it's a little bit like art, isn't it? You know, an artist fashioning his painting, except we're doing it a lot differently than those guys do. Alright, so at 1/2, y at 1/2 is minus, here's 1/2, minus 1.84 is about here. And the Y-intercept was very close to that, just a hair above it. There we go. So 1.8, 1.84. Is that okay? All right. Now then, so now we can do a pretty good sketch. So left of -2, it's decreasing concave down. So it's coming down like this, but then it changes to increasing concave up. Boy, well, I'm a little worried about that. I don't think this is going to work. Because it's supposed to come down here and nail that, isn't it? So, do I have a mistake here? Ooh boy. All right. Well, if I have a mistake, I don't know if I'll keep this video. But if you're watching this video, I kept it just to show you my mistake. And let me double check that again. If I plug in 0 into the first derivative, do I get a positive? This is negative, that's negative, I get a positive. It's increasing there. Okay, so here's what I have. It's decreasing concave down. And then it's supposed to start increasing concave up. And which means it goes like this. But now it's not going to come down and grab these. So I got a big mistake. Well, there was a mistake. I found it. Fortunately, it's pretty easy to correct. You've probably been screaming at the screen here. It was here, wasn't it? I forgot to write a 2 squared. Well, that changes things, doesn't it? That changes things quite a bit. All right, so this needs to be squared in order to get a 5 here. So it's 2/3, and we take the derivative, we get 5/3. Negative 2/3, then down to minus 5/3. All right, so please fix that too in your notes if you haven't done so already. And I debated about whether just to start fresh from this video or not, and I decided to keep it because otherwise I'm happy with my work, and it's a lot of work. But we run into these problems. You know, we all make these mistakes. Even I did, but you got to learn how to catch them. So it's a great, I think it's a great moment because what I have here doesn't work. Decreasing concave down, that's good, but then it's supposed to increase concave up, and if it increases, how's it going to catch these 2 points? Okay, not going to work, is it? So we do have to find the error. Hopefully not start over. Now in this case, I just need to recalculate the signs of my first derivatives. So let's go back, and I'll get that fixed, and then we'll finish drawing the graph and be done with it. So anyway, it's a long video for one problem, but I think it's well worth it because there were a lot of interesting things in this graph. Alright, so I gotta go back and, let's see, type this in. So parentheses 2x minus 1, close parentheses, divided by 3, divided by parentheses x squared minus x minus 6, close parentheses, raised to the parentheses 2/3, 2 divided by 3. Alright, so now I'm not sure if this is going to capture the correct sign, so I have a little bit of doubt here. Let me plug in 0 just to check myself. 0 store x, because this might be a calculator moment. I got a negative number. Alright, so if I plug in 0 here, I get minus 1 over the cube root squared. The cube root squared is positive, and so the numerator is going to be a negative here. So, and I got a negative on my calculator. In fact, I'm wondering, why am I using the calculator on this? Why? Because, you see, this part is positive. When you're squaring this number, the cube root could be a negative. When you square it, it's a positive. So the only thing we're worried about is the numerator. No matter what sign this is, the positive denominator is not going to change it, is it? And so, if I plug in like negative 3 minus 1 is negative 7, I have negative 7 over something that's positive. It's a negative number. So it's decreasing. And then if I plug in something like 0, if I plug 0 in, I get negative 1 over something positive. So that's a negative number. It's still decreasing. And then when we jump over past 1, over here, put 1 in, I got 2 minus 1 is 1. Positive number over positive number is positive. And if you go past 3, 4, put 4 in, you get 7 over something positive. Alright, so you can punch those in on a calculator, but I just saw that, well, when the sign of the denominator is always fixed, then all we have to worry about is the numerator. Especially if the denominator is always positive, it makes it easy. Alright, so it better correct this. It went negative, negative, then plus, positive. So it decreases on the left half, increases on the right half. Alright, and I've seen this graph. I know it's supposed to do that. So okay, so we this didn't change. It's decreasing concave down. So we're on this half of the concavity. Now it's decreasing concave up. So it comes down like this, down to the relative minimum. Actually, that's the absolute minimum, isn't it? And then it's going to start increasing concave up. So loop up this way, all the way over to here. And then it's going to increase concave down. So it's going to go. Actually, to do a really better job of this, and I'll explain that in a minute. Let me change this loop a little bit. See if I get a little more accurate here. Okay, so it goes straight up like that, and then increases concave down. All right, there we go. So whatever that is, it kind of dips down, goes up. It reminds me of a part of the bike trail between Washington Courthouse and Chillicothe. There's two of these. They're not quite that steep, but there's two really nice big dips where you can really get your bike up to good speed. Anyway, that kind of reminds me of that. There we go. So in all its glory, there is the graph of a cube root of a quadratic expression, and this one came out this way. So I have I did this on my computer. Just I wanted to see what it looked like before I started this, and that's exactly what it is. So I will probably put a link on YouTube, my YouTube page, to this, or the home page for these videos. I'll try to remember to put a link to this, to the computer drawing of this, which is a little better in mine, of course. All right, well, there was that problem. Wait, not so fast. I thought of one other thing here before we erase all this big masterpiece. You remember over here where we determined that these two critical points in the first derivative cause division by 0. And well, this is what happened here. This is why this comes down vertically. So at this point and at this point, you have vertical tangent lines. So that describes that behavior. And you want to reflect that in case you end up with this in a graph. You want to make sure that really shows, rather than just go, you know, sideways like this. It wouldn't show that feature. So you want to make sure that feature is shown there. Okay, now let's go on to a new problem.